talk. All right. So I'm very happy to introduce my colleague Hugh Woodin and give this lecture for the Tsinghua CMSA lecture on the history and the literature of mathematical science. This was started 2 years ago by Xintong Yao and initiated this program. And so I would like to say a few words about my colleague and good friend Hugh. And he was get a Bachelor of Science degree from California Institute of Technology and get a PhD at Berkeley. And he was a professor at Caltech and also a distinguished professor at Berkeley and served as the chairman twice. And since 2014, he went to Harvard in the joint appointment in philosophy and mathematics. He received many prizes. I will only mention a few of them. He was elected fellows of American Academy of Art and Science, and he also received these household medals for European Society. And he's honorary professor for the Chinese National Academy of Sciences. He gave many distinguished lectures, and there are many of them. I will only mention one of them, which he gave 3 lectures in the ICA, including 2 invited lectures and 1 plenary lecture. Hugh was known very much for his famous work on the Woody Cardinals and also for the continuum hypothesis. So I'm sure he will say some of them today. So let's welcome Hugh.
Thank you, HT. And I want to thank the CMSA for this opportunity. Thank all of you for coming, especially in Beijing. I realize it's late there. Okay, this is supposed to be a history lecture, and I'm terrible on history. I'll have dates in, but this is going to be a historical view from one perspective. We'll be talking about large cardinals and small sets. All right, so let's start with the basics. We have the ordinals, the transfinite numbers. The empty set is 0, that's 1, that's 2. Alpha is an ordinal, it's just a set of smaller ordinals, and you get the next ordinal by adding alpha as an element. That's alpha plus 1. Omega, the standard denotes the least infinite ordinal. It's a set of all finite ordinals. So if you have any formal property of ordinals and it holds of some ordinal, it holds for a least one. That's induction. For those who couldn't see, I just defined the ordinals. Those are the first 3. Alpha is an ordinal. Alpha plus 1 is gotten by adding alpha to the set alpha. Omega is the least infinite ordinal, set of all finite ordinals. Important to note, ordinals do not measure cardinality. They measure the lengths of well orderings. I guess the people in Beijing can't see my fancy laser pointer. Oh well. The ordinals provide the basis for transfinite induction. So sets ZF. ZF is ZFC without the axiom of choice. A fundamental operation on sets is the power set. Given a set X, you can form the set of all subsets of that set. That's called P of X. That's exponentiation in sets. And from the axioms, the power set exists for every set. With that in place, we can layer the universe of sets in the cumulative hierarchy. And this is done by defining V alpha by induction on the ordinal alpha. So we start with just nothing. At the successor step, we take the power set of what we've constructed. And at limit stages, we take the union. This is a unique construction by induction. And by the ZF axioms, if X is a set, then there must exist an ordinal alpha such that X is in V alpha. In fact, if you take this as your conception of V, it's not hard to get to the ZF axioms. They're kind of follow naturally from this conception. Maybe not the axiom of choice, though. Well, if we want to move beyond the basic axioms, these are large cardinal axioms. The ZFC axioms can be augmented by axioms that assert the existence of very large infinite sets. These are called large cardinals, and here's a list. Increasing strength in some sense. So the bottom for this, our purposes are measurable cardinals. I will discuss a smaller large cardinal notion later, and we go all the way up to near the ceiling, the axiom I0 cardinals, which I'll mention at the end. And I'm not putting this here just because it's irrelevant, it will play a role. So there are, of course, earlier conceptions of mathematical infinity, and might want to see how it fits into the universe of sets. So if you take number theory, one of the classical structures of mathematics, mathematically, that's just V omega with the membership relation. If you take second order number theory, kind of the next move into the infinite, that's mathematically just V omega plus 1. And then if we go to third order number theory, which is the reals with all sets of reals, that's just V omega plus 2. So a lot of mathematics lives way down in the bottom of the cumulative hierarchy. And then there's Cantor's theorem that if n is a set of all natural numbers and r is a set of all real numbers, they do not have the same cardinality. So infinity comes in different sizes. This began set theory and led to Cantor's continuum hypothesis that if A is an infinite set of real numbers, then either it has the same cardinality as the natural numbers or the same cardinality of the real numbers. I want to say a little bit about the axiom of choice. That's a kind of an outlier axiom. I've already said that doesn't flow naturally from the initial conception of V. So what is the axiom of choice? Well, if you have a subset A of x cross y, then a function is a choice function if for all points in x, if there is a point in y such that the pair belongs to A, then A f of A is in that set. So it chooses in every vertical section an element if there is one. Axiom of choice. And the axiom of choice just asserts that for every set, there's a choice function. Now, there's a standard variant of the axiom of choice, that's a well-ordering principle, that every set can be well-ordered. So if you have a well-ordering as a linear order where every non-empty subset has a least element. And then you have implicitly Zermelo's theorem. Now, he proved the theorem before the ZF axioms were actually isolated, so that's why it's after Zermelo, but it's his proof. The following are equivalent, the axiom of choice and the well-ordering principle. And I think in modern times, most people think of the axiom of choice as a well-ordering principle, but there is a difference, and that difference will become important. Well, the axiom determinacy emerges. So the equivalence of the well-ordering principle and the axiom of choice does not hold if one restricts to subsets of R cross R, or even to subsets of R cross V. And what's the problem? And what do I mean by that? Is if you assume the axiom of choice for R cross V, in other words, R cross X for all sets X, you can't prove that there's a well-ordering of the reals. You really need the axiom of choice for subsets of P of R cross R to get a well-ordering of the reals. So that opens a door for having a restricted fragment of the axiom of choice, and maybe not all the pathologies that are commonly associated with the axiom of choice, such as non-Lebesgue measurable sets. So what's determinacy? Given any set of real numbers, you can associate to the set an infinite game. There are many ways to do this. Here's one way. The players alternate choosing 0 or 1. After infinitely many moves, this defines an infinite binary sequence. Player 1 wins if that real number is an A, otherwise player 2 wins. So they're just playing a binary expansion. A is determined if there's a winning strategy for one of the players in this game. Now, what's a winning strategy? It's a function that tells the player how to play given what's been played so far. So the state of the game at any round is just a finite sequence of zeros and ones. So strategy is just a function from finite sequences of zeros and ones to either 0 or 1. And if the player uses that function and always wins, uses that function to select their moves and always wins, no matter how the other player plays, that's a winning strategy. So it's not clear that for non-trivial sets A, they are determined, because A could be very complicated and a strategy has only a countable amount of information in it, being a function from finite binary sequences to 0 and 1. And then there's a Gale-Stewart theorem from 1953 that if A is open, it's determined. And they asked whether more complicated sets could be determined, provably. So AD emerged as an alternative of the axiom of choice. I'm sorry you can't quite see the header. So if you assume the axiom of choice, there is a set which isn't determined. And the reason is you just well order the reals, and then you build a set by putting things into A and keeping things out of A, and you diagonalize against all the strategies. The point is that for a strategy to be winning, it's making continuum many commitments about the set or its complement. So you have enough room to defeat all possible strategies as winning strategies. But that doesn't mean one shouldn't consider the axiom of determinacy, which is that every set is determined. And it's an interesting axiom. It implies every set's Lebesgue measurable. And Mycielski and Steinhaus in '62 speculated that maybe AD is the correct axiom for the structure of P of R, which, if you recall, is really V omega plus 2. And so this would be an axiom for the universe of sets without the axiom of choice. You can't have the well-ordering principle. But maybe you don't want the well-ordering principle if you're just interested in the structure of P of R. So I want to give you some idea of just how powerful this axiom is. It really has amazing consequences. So let's put a metric on n to the n. Now, for me, the natural numbers for this talk start with 1. Omega is the natural numbers together with 0. This is controversial, whether you start with 0 or 1. I wrote a book with an analyst, and we had long battles over whether one should start with 0 or 1. So let's put a metric on it. The distance from x to y, this is when x is not equal to y. It's just 1 over n, where n is least, such that x of n doesn't equal y of n. Now, if you start with 0, then add 1. So this is a complete metric space. Its diameter is 1. And now let's make a definition. We have two subsets of n to the n. So with this, we say A is reducible to B if there's a continuous function from n to the n to n, such that A is the preimage of B by that continuous function. But we require that the function is a Lipschitz function with order 1. In fact, we require that the distance from f of x to f of y is less than or equal to the distance from x to y for all x, y. We'll say A is strongly reducible to B if you can choose f here so that it's a retraction, that the distance from f of x to f of y is always less than or equal to 1/2 the distance from x to y. So it's just like reducibility, but we require that the function be a retraction. Early days of AD was a great time. You think of the right game, you get a PhD thesis. So there's Wage's lemma from '72, assume AD, suppose you have two subsets of n to the n, then one of the following hold. A is reducible to B, or the complement of A is strongly reducible to B. And I have a typo there. It should have been A is reducible to B, or the complement of B is strongly reducible to A. So it's amazing how many times one can look at slides and still have typos. I guess one sees what one thought one wrote and not what one actually wrote. Okay, so that's an easy, it's an easy lemma. You just think of the right game. You have to find the right subset of n to the n, and somehow you build that from A and B. Maybe I should have said that n to the n with this metric is homeomorphic to the Euclidean space of irrational numbers. Now, no set can be strongly reducible to its complement, because if you have a function that satisfies this condition, it has to have a fixed point. And that's easy because the space has diameter 1, so the range has to have diameter 1/2. But the only way two functions can have distance at most 1/2 is if they agree in the first coordinate. Then you take the range of the range, now the width is 1/4, you have agreement in the first two coordinates and so forth. But a set can be reducible to its complement, just can't be strongly reducible. Just look at all of the points in x to the n such that x of 1 is even, then A is reducible to its complement by an isometry. You just flip. So this leads us to the wage hierarchy, in particular the wage trichotomy theorem. We now assume AD. If we have two subsets of n to the n, then exactly one of the following holds. A is reducible to B and B is reducible to A, or the complement of A is reducible to B and B is reducible to the complement of A, and possibly both of these hold. For example, if A were reducible to the complement of A, as we just saw, then these could both hold. These would both hold. Second possibility, these are mutually exclusive, is that A and the complement of A are strongly reducible to B. Third possibility is the other way around. B and the complement of B are each strongly reducible to A. These are mutually exclusive because if two of them held, you'd end up with a set being strongly reducible to its complement. One thing to keep in mind is that if you have a chain of strong reductions, A1 is reducible to A2 ... reducible to AN, and any one of those reductions is a strong reduction, then A1 is strongly reducible to AN. Okay, so that's the trichotomy. And then that's what we've done in effect is define a preorder. We'll define A to be equivalent to B if 1 holds, and we'll define A to be less than B if 2 holds. So this is an equivalence relation on subsets of n to the n, and then an ordering of the equivalence classes. It's a preorder. Okay. Well, is the preorder a pre-well order? In other words, can we have an infinite descending sequence under strong reducibility? And there's Martin's theorem from 1973. Assume AD, there's no infinite sequence such that for all I less than omega, AI plus 1 and its complement are each strongly reducible to AI. There's no strictly decreasing sequence in the wage preorder. And maybe it's interesting to note that you don't really need AD here. I mean, you just need that every set which is reducible to A0 has the property of Baire, or if you want, every subset which is of n to the n, which is reducible to A0 is Lebesgue measurable. You can do it both ways. You know, so for example, if A0 were Borel, this condition applies, and so Martin's theorem applies to all infinite sequences of Borel sets. Now, suppose that every Borel set is determined, then the wage trichotomy theorem holds for the Borel sets. This order, which is well-founded by Martin's theorem, is a very fine layering of the Borel sets. If you look at the Clopin sets in this space, those are the ordinals of countable rank. So we normally think of the Borel sets as an omega-1 hierarchy. This is much finer than the usual hierarchy on the Borel sets. Well, remember, Gale and Stewart showed that if A is open, A is determined. That implies that the wage pre-well order is defined on all the Clopin sets. If you go back to Wage's theorem, Martin showed in 1975 that if A is Borel, then A is determined. And so the wage pre-well order is defined on all the Borel sets as a theorem of ZFC. Remember, it's a very fine, then we have Martin's theorem that tells us it's a pre-well order, so we have a very fine hierarchy. But with AD, this extends to all sets. So it's an incredibly fine hierarchy on the borel sets, but the borel sets are an initial segment of a much richer and longer hierarchy in the context of AD. All right, but there's an asterisk on Martin's theorem. Friedman showed in 1971, that was before Martin's proof, that borel determinacy cannot be proved in Zermelo set theory. Zermelo set theory is ZFC without the axiom of replacement. If you look at V omega plus omega, that's a model of Zermelo set theory. So that's a little astonishing. Why should the proof of borel determinacy go beyond P of R? The thing, all you need are the reals, maybe you need sets of reals, but you need much more. All right, what about the axiom of choice question? So a pre-order on the reals is a pre-well ordering if every non-empty subset of A has the least element with respect to that pre-order. So a pre-order on A is an equivalence relation on A with a well ordering of the equivalence classes. We've already seen a pre-well order, but the wage pre-well order is on P of R. We're now shifting to pre-well orders on R. Okay, now I have to make a somewhat technical definition. This is really due to Moskovakis of 1971, and it's the notion of a scale on a set. So it's a sequence of pre-well orderings. Remember, pre-well orderings are equivalence relations with a well ordering of the equivalence classes. So this says that the equivalence relations are refining each other. So the equivalence classes of the later pre-well orderings in this list sit inside the equivalence classes of the earlier one. So if you think of maybe the first pre-well ordering has just one equivalence class, it's trivial. Then the next one might have some number, and then you just keep shrinking the equivalence classes by introducing more equivalence classes, refining the order, and that's all that. That's what that's saying. Now the technical condition. Suppose you have an infinite sequence of non-empty subsets of A with limit point X in the natural sense. That means every neighborhood of X contains a union of the tail. Okay. Suppose that these things are all getting more and more equivalent. So for all I less than omega, Y is I equivalent to Z, that's relative to the ith pre-well order for everything in the union of these sets for K greater than or equal to I. So the tails, the union of the tails are living inside the equivalence classes. Then the conclusion is that X is in A, and that's really all I'm interested in. But then you say X is less than or equal to I equivalent to Y for every Y in the union of the tail. So if you unpack this, what we're really doing is putting a well-ordered topology on A that's making A closed. That's really what's going on. But this is a nice way to view, an important way to view this, okay? Now, for those of you familiar with scale, you might say, well, wait a minute, that's not the normal definition. It would be if you had a sequence of reals. In other words, these would be singleton sets. But you have to be a little careful in the choiceless universe. You can have possibly an infinite set of reals which contains no non-trivial convergent sequence. In other words, a Dedekind finite set of real numbers. If you had a Dedekind finite set of real numbers, I could make all these pre-will orderings the same and with one equivalence class, namely A, and this condition would be satisfied vacuously. So that's why I changed that way. And the reason I did that is I wanted to note this lemma. If you have a subset of R cross R and there is a scale on A, and that's defined the same way as a scale for subsets of R. In our case, if we view R as n to the n, R cross R and R are homeomorphic. Obviously, that's not true for the Euclidean space. We define a scale for subsets of R cross R the same way. Then there's a choice function. That's in ZF. So scale opens the door for getting fragments of the axiom of choice. What about our familiar sets? If A is Borel, it actually has a scale where all the pre-will orderings are Borel. And the reason I say ZFC here is without the axiom of choice, you have to be careful how you define the Borel sets. There are two different ways to define the Borel sets. And to eliminate that ambiguity, I've just put choice. So the speculation is maybe we can retain the axiom of choice for subsets of R cross R, but also have that all sets are Lebesgue measurable, or maybe even all sets are determined. Remember, we can't have, this shows that you can get choice functions from scales, but scales don't give you well orderings. So it's not, it could be that every set has a scale, every set of reals has a scale, is compatible with all sets Lebesgue measurable. And we'll see that. Well, now we want to move beyond the Borel sets. So we go to the projective sets, and there are two mathematically equivalent ways to define the projective sets. You can do it with logic. These are the sets of reals which can be logically defined in that structure from parameters. I view the reals as a subset of V omega plus 1. You can do it with calculus and look at all the sets of reals that can be generated from the initial set R of all reals in finitely many steps using two very simple operations. You're allowed to take the complement, and you're allowed to take the image by a function, and that function is required to be continuous when restricted to the space of all irrational numbers. And so the idea here is there's really only a countable amount of information in such a function, right? You have the values on the rationals, which can do anything they want. But then on the irrationals, the function is uniquely determined by its values on any dense set. So, for example, on the rational translates of pi. So we could focus on the projective sets. Projective determinacy is assertion that every projective set is determined. Now, this is not obviously contradictory with the axiom of choice. We don't know. But we can investigate the axiom. We get that every projective set, so if you assume projective determinacy, every projective set has a property bare, it's Lebesgue measurable. Those are just localizations of the AD theorem. But then you get the continuum hypothesis holds for the projective sets. Now that's starting to give us some set theoretic information. And then a deeper theorem is that every projective set has a projective scale. And that means every projective subset of the plane can be uniformized by a projective function. So we have a little like arena of the projective sets. If we assume PD, we get some version of the axiom of choice from this, but we also get regularity properties such as measure and category. So we'd like to move beyond now the projective sets. So the definable power set is a P def for definable of X is a set of all Y contained in X, such that Y is logically definable in the structure X with membership with parameters from X. So P def of X is a collection of those subsets of X which are somehow intrinsic to the set X itself. You only need to see X to figure out the definable power set versus the power set of X, which in general is which is by definition all subsets of X, and that depends upon the ambient universe of sets, particularly if X is infinite. So Gödel had the idea that we should revise the cumulative hierarchy. And the change is at the successor step, you start the same, but at the successor step, you take the definable power set instead of the full power set. If you take the full power set, you get the V alphas. And limits, you take unions, and then L is the class of all sets that belong to L alpha for some alpha. So again, if this was the full power set, these would just be the V alphas, and L would be V. So we're finally calibrating, we're restricting the power set. Okay, now Gödel did this for a number of reasons, which I'm not going to talk about. He showed that in L, the ZFC axioms hold. The definition does not need the axiom of choice. So that shows that if ZF is consistent, then so is ZFC. And he also showed that CH holds within L, even if CH fails in V. I'm not going to say anything more about that. Okay, now we'd like to generalize a little bit further. The collection of the projective sets is exactly the power set of reals intersect the definable power set of P def, definable power set of V omega plus 1. So this suggests a generalization now of the projective sets. So given a set of reals, we define L alpha of A and R by induction on alpha exactly as the definition of L, except we alter what we start with. Instead of starting with the empty set, we start with the reals together with A. So we're putting in all the reals and we're putting in A, and then we're just iterating with the definable power set. Okay, so these are the sets of reals that are somehow intrinsic, must exist, given the ordinals and given that A exists, given that you have A. If you take A to be empty, then P of R intersect L of R now. A is empty, so L of A and R just becomes L of R. That's a transfinite generalization of the projective sets. If every set in P of R intersect L of R is determined, and we go to the universe L of R, that's a model of the ZF axioms together with AD. And this is really the modern view of the issue with AD. It's not an axiom for V, it's an axiom for a fragment of V. L of R is the simplest fragment of V that has the ZF axioms and contains the reals. So this would be the simplest fragment to look at to try to find a fragment in which AD holds. What about scales? We had all that information about scales for the projective sets. Well, Soloway observed that the following are equivalent. Every set that's in L of R has a scale in L of R. And the axiom of choice holds in L of R. So if you assume AD, all the sets in L of R are determined, that's what that means. There has to be a set in L of R that has no scale in L of R. It's not going to be as nice as the projective sets. Well, so we need to invoke some definability. So X is sigma 1R definable if for some formula in the language of set theory, X is a set of all A, such that there's a transitive set such that R belongs to A belongs to M, and the structure M with membership thinks that formula holds of A and R. So it's a relative definability to R, and I'll remind you that a set is transitive if every element of M is a subset of M. A transitive set is like an initial segment of V. Why transitive? Well, Y, an element of X, an element of Y, implies Y is an element of Y, M. So this is logic, and definability is now going to start playing an important role in the story. So now with that definition, we can specify the extent of scales in L of R. So it's the Martin-Steele scale theorem from 40 years ago. Assume ADL of R, suppose A is in L of R and A is sigma 1R definable in L of R. And that's not the same as being sigma 1R definable in V. Okay, we're doing the restricted form of definability in L of R. Then A has a scale in L of R, which is also sigma 1R definable in L of R. And this is the best possible by localizing or analyzing Solovay's observation. They also prove something else, a basis theorem. Again, ADL of R, but now we look at subsets of P of R, which are sigma 1R definable in L of R, and that X is non-empty. Then X has a member such that both A and its complement are sigma 1R definable. So a sigma 1R definable collection of sets of reals has an element which is not only sigma 1R definable, its complement is sigma 1R definable, assuming X is not empty. And then another thread emerges, which is getting determinacy from its consequences. So if you look at Gödel's analysis of L, so you get the following theorem. Suppose R is contained in L. In other words, that L of R is L. then the conclusions of the Martin-Steele scale theorem and the Martin-Steele basis theorem both hold. So the theorem that Martin and Steele proved about L of R actually is true in L. But now there's an amazing characterization proved 30 years ago. Suppose that for every set of reals, if X is an L of R, then X is Lebesgue measurable. In other words, we deny the axiom of choice explicitly. Then the following are equivalent. AD holds an L of R, and the structure, the conclusions of the Martin-Steele scale theorem and the Martin-Steele basis theorem both hold. So this says that in the restricted setting of L of R, with a regularity assumption on the sets there, AD is equivalent to its structural consequences. So that's determinacy from its consequences. Well, now we'd like to move beyond L of R. So ZF denotes the axioms of set theory without the axiom of choice. Okay, now we want to bring in some weak fragment of the axiom of choice. DC is the axiom that for all partial orders, one of the following holds. Either there's a point in P, A and P, with nothing smaller, or there's an infinite descending sequence. Okay, and then DCR is DC for partial orders on the reals. So DC just says if you have any partial order, you can find a point with nothing smaller, or you can build an infinite decreasing sequence. DCR is just DC, but you only look at partial orders on the set R. That partial R has nothing to do with the usual ordering of the reals in general. V is L of P of R is the axiom which asserts that V is L of V omega plus 2. Now, I didn't define that, but you can guess what the definition is. You can relativize L to any set, any transitive set. So the natural axiomatic setting for generalizations of AD is ZF plus DCR plus V is L of P of R. So if we want to move beyond AD, there's ADR, that's the assertion that all games given by subsets of R to the omega, that's sets of infinite sequences of reals, are determined. The game now, the players alternate choosing reals instead of choosing elements of 0, 1. And strategies now are functions from finite sequences of reals to reals. Uniformization is the assertion that the axiom of choice holds for all subsets of R cross R. It's a trivial observation that ADR implies uniformization. You just play the game in one round. Uniformization implies DCR is also easy. So this is kind of a cheat. It's the reason ADR implies uniformization is because you have to have strategies. Now you might say, well, what about the determinacy of all games given by subsets of omega 1 to the omega? Here, omega 1 is the least uncountable ordinal, and the players would play countable ordinals. That axiom is inconsistent. ZF just proves there's a subset of omega 1 to the omega which is not determined. What's curious about that proof is it's not necessarily a definable set. You can't exhibit it in general. All right, I won't be giving that many more definitions. Infinity Borel codes. We'd like to define a transfinite generalization of the Borel set. So we do that first by defining the codes. All increasing pairs of rational numbers are infinity Borel codes. If S is an infinity Borel code, we pair it with 0. That's an infinity Borel code. And any transfinite sequence of infinity Borel codes is an infinity Borel code. So infinity Borel codes are recipes, and they're basically sets of ordinals. So how do we interpret an infinity Borel code? Well, if you have a code here that's an increasing pair of rationals, it's just the interval with those endpoints. If S is the code gotten by 0t, then the interpretation of S is just a complement of the interpretation of T. If the infinity Borel code is given by a well-ordered by sequence of infinity Borel codes, then the interpretation of S, the set A sub S, is the union of the interpretations of all the sets in the sequence, codes in the sequence. So it's a recipe. And it's either telling you what the basic simplest sets are, telling you when to take a complement and when to take a union, but everything is, and we would say logically effective. A set of reals is an infinity borel if there is an infinity borel code such that X is the set, the interpretation of that code. So why do this? Well, if you assume the axiom of choice, every set is infinity borel, so it's not an interesting notion. One can prove in ZF plus DC that the sets generated from the initial set R, I'm going back to the construction of the projective sets, in 4 steps of taking continuous images or complements are infinity borel. But you can't prove that the sets generated in 5 steps are infinity borel. So infinity borel becomes an interesting notion, possibly in the context without the axiom of choice. Another, what about scales? If A is a set that has a scale, then it's infinity borel. So infinity borel is a weakening of the notion of scale. If A is, so is it interesting though? If A is infinity borel and there's no uncountable set of reals which can be well ordered, then A is Lebesgue measurable and has a property of Baire. So in the anti-choice environment of no uncountable well-ordered set of reals, the infinity borel sets are very nice. So the infinity borel sets form the basis for a technical refinement of AD that emerged over a 5-year period, again, almost 40 years ago. We're working in our base theory, ZF plus DCR plus V is L of P of R. Then AD plus, that's this technical refinement, holds if the following holds. Suppose you have a pre-well ordering of the reals of length theta, and you have a continuous function from theta to the omega, where you give theta the discrete topology, into omega to the omega, where you give omega the discrete topology. So this is just n to the n up to homeomorphism. Then for every subset of omega to the omega, if you take the pre-image by this function, the game on theta is determined. So this is trying to do, we can't assume the determinacy for all subsets of theta to the omega. That's inconsistent if theta is bigger than or equal to omega 1. But we're focusing on just those sets that arise in a certain special way. Okay, so that's the first component. And then the second component is every set's infinity borel. So it's a form of determinacy together with a structural assumption that every set is infinity borel. AD plus trivially implies AD, just take the identity function. And then the pre-image of A is just A, and the game is on omega. Okay, is this a useful axiom? So again, assume our base theory. Suppose A is contained in R. I'm working in this theory now. And A is sigma 1 of R definable. There's no L of R here. Then A has a scale, which is sigma 1 R definable. So the Martin-Steele theorem generalizes in AD plus. So does the basis theorem. Suppose that X contained in P of R is sigma 1 R definable and X isn't empty. Then X has an element A, such that both A and its complement are sigma 1 R definable. So it generalizes the Martin-Steele theorem from L of R, which is possibly very restricted in the context of AD, to essentially no restriction whatsoever, but you have to assume AD plus. And this leads us to the first equivalence theorem for AD plus. That was what was hiding there. Again, we assume our base theory, assume AD, the following are equivalent. AD plus and the conclusions of the AD plus scale and basis theorem both hold. So the AD plus allows you to generalize to get the AD plus scale and basis theorem. It's actually equivalent in the context of AD. Corollary, assume L of R satisfies AD, then L of R satisfies AD plus because of the Martin-Steele scale and basis theorem. There are other proofs of that, but assume our base theory and assume that every set has a scale, then AD plus holds. So we get AD plus in the context of AD from the assumption that every set has a scale. But we don't know if that's possible. And that leads to the second equivalence theorem, same base theory. Assume AD, the following are equivalent. Every set has a scale, ADR, uniformization. So in the context of AD, uniformization only comes from scales. Remember, uniformization is that fragment of the axiom of choice. Another corollary by the previous theorem, assume ADR, AD plus holds. Because in this theory, ADR implies every set has a scale, and the previous theorem was if every set has a scale, then AD plus hold. So this was the first evidence that every set could have a scale in the context of AD. It was not clear from the previous theorems for AD plus whether that was a consistent hypothesis. Maybe the L of R theorem, Solovey's theorem about L of R, that not every set has a scale, maybe that was an AD theorem. Okay, so the conjecture is that in our base theory, AD implies AD plus. And that's open. Okay, what about large cardinals now? This is supposed to be about large cardinals and small sets. Assuming the axiom of choice, there is a set which is not determined. Maybe one doesn't need the axiom of choice. Maybe PD is inconsistent. That would kind of trivialize everything I've said. The Martin-Steele theorem from nearly 40 years ago, if there are infinitely many Woodin cardinals, then PD holds, and shortly thereafter, if there are infinitely many Woodin cardinals with a measurable cardinal above, then AD holds an L of R. So large cardinals imply they're rich fragments of the universe of sets in which AD holds. Okay, small large cardinals, though. The cardinal kappa is strongly inaccessible. If the following holds, bigger than omega, cardinality of V alpha is less than kappa for all alpha less than kappa. If X is a subset of kappa and it's cofinal in kappa, remember cardinals are ordinals and ordinals are linear orders, then the cardinality of X is equal to kappa. So kappa is supposed to look like omega. So strongly inaccessible large cardinals. Strongly inaccessible cardinals are large cardinals. If kappa is strongly inaccessible, then V kappa already models all of the ZFC axioms. But they're small. If kappa is inaccessible, then kappa is strongly inaccessible in L. So small means they're compatible with L. Okay, so now I want to bring in another thread. This goes back to Solovey, the symmetric collapse extension. Suppose V of G is a Cohen forcing extension of V and R star is a subset of the reals of V of G. Then V of R star is a symmetric collapse extension of V at gamma. If the following hold, gamma is a strong limit cardinal in V, that means the cardinality of P of alpha is less than gamma for all alpha less than gamma. Every ordinal less than gamma is countable in the enlargement, V of R star. For all X and Y in R star, if I add X and Y to V and look at the reals I get, that's included in R star. That's a closure condition on R star. And then there's a genericity requirement. Every X in R star is V generic for a partial order in V whose cardinality is less than gamma. So R star lives in some generic extension of V of G, but there's no requirement on what the size of the associated partial order is. So this is basically Solovey's famous result from 1965 and all sets Lebesgue measurable reinterpreted. Suppose V of R star is a symmetric collapse extension of V at gamma, so it has all those properties. Then the following holds. V of R star models all sets of Lebesgue measurable. V of R star models every set as infinity Borel. So infinity Borel was not an isolated notion when Solovey proved his theorem, but his analysis shows that. Suppose gamma is strongly inaccessible in V, then V of R star models DC. And that's Solovey's all sets Lebesgue measurable theorem. It says you can have all sets Lebesgue measurable together with DC if you're willing to grant the possibility of a strongly inaccessible cardinal. But now there's a connection with AD plus. This is the derived model theorem, and it emerged over 7 years, sharper versions. Suppose gamma is a limit of Woodin cardinals, it's a strong limit then, and V of R star is a symmetric collapse extension at gamma. So let gamma, the font issue, be the collection of A contained in R star, such that A is in V of R star, and L of A in R star models AD plus. So we're going to the symmetric collapse extension and collecting all the sets of reals so that if we construct from them, we get AD plus. Then if we construct from the whole collection, we have AD plus. So there's a maximum AD plus model in V of R star, and that defines it. This is called the derived model of AD plus given by V of R star. So in the symmetric collapse extension at a limit of Woodins, there's a maximum AD plus model. And in particular, there is an AD plus model because if there weren't, even if this set was empty, we'd have L of R star models AD plus. So this can't be empty. So that's the derived model. And this brings us to the first AD plus duality theorem. And this, well, here's the theorem. It's basically saying every AD plus model is a derived model. So if M is a countable transitive set and it models our base theory, that's what this, and this is, but it also models AD plus, then there's a countable transitive set N. Omega 1 of this model is a limit of Woodin cardinals in N. If you take N and add the reals from M to it, that's a symmetric collapse extension of N at Omega 1 of M, which is a limit of Woodins. And M is a derived model of AD plus associated to N of together with the reals from M. So the slogan is every countable AD plus model is actually a derived model. Now this theorem was proved in all cases except for one over 30 years ago. That's 91. The only remaining case was when M satisfies this, well, that's this, and then M also satisfies the axiom of choice for subsets of R across P of R. That was the one case that was open. And so that was solved last year. Okay, the last player, I have two more main definitions. Gödel's transitive class HOD. So HOD is a collection of all sets X such that there exists an ordinal alpha. M belongs to V alpha. X is in M. M is transitive. Remember, every set's transitive of every element of the subset. And every element of M is definable in V alpha from ordinal parameters. So this is a mashup of kind of definable power set in the V alphas. We're looking, okay, so that's the definition of HOD. The axiom of choice holds in HOD, whether or not the axiom of choice holds in V. That's one reason Gödel was focusing on this. And now there's a connection. Assume our base theory is ZF, but I'm going to assume ADR plus V is L of P of R. Let's let theta be the supremum of the lengths of all the pre-will orderings of R. Then theta is a limit of Woodin cardinals and HOD. Remember, the axiom of choice holds here. So we're in a V where we have ADR, and we're getting a ZFC model, in fact, a canonical model, in which theta is a limit of Woodin cardinals. So there's a second connection of AD plus with large cardinals that's beyond the first duality theorem. And this brings us to the inner model program, which starts with Scott's theorem. Assume V equals L, there are no measurable cardinals. So measurable cardinals aren't small. The inner model program seeks to construct enlargements of L in which large cardinals can exist. These enlargements are called core models. The stronger the large cardinal notion, the harder the problem. So there was a remarkable convergence 30 years ago, and surprise. So assume AD L of R now, and let theta be the supremum of the lengths of the pre-well orderings in L of R. First theorem was that theta is a Woodin cardinal on the Hod of L of R. This is the L of R version of the previous theorem. Previous theorem was theta, it's defining theta the same way. It was a limit of Woodin cardinals, but ADR doesn't hold here. Theta can't be a limit of Woodin cardinals in this Hod, but theta itself is Woodin. In the previous theorem, theta can't be Woodin. Okay, so now we have a remarkable convergence. Steele proved that the Hod of L of R intersect V theta is a core model. So what the intermodal program was seeking to construct occurs naturally. That's a remarkable convergence. Well, what's the surprise? Hod of L of R is not a core model. It's something called a strategic core model. So what AD plus is doing is it's identifying a new class of enlargements of L, and these are the strategic core models. There was no hint that these existed before. And this brings us to the AD plus duality program. This is not an official, well, it is now an official program. The main current goal of the AD plus duality program is to prove the following conjecture. Assume ZF AD plus DC plus V is L of P of R. That's, in other words, AD plus. Hod is a strategic core model. And it's important here that you add this, otherwise the conjecture is false. What about the intermodal program? The large cardinal axiom that there's a supercompact cardinal has emerged 30 years ago as a pivotal case for the intermodal program. There's another surprise that emerged over a 2-year period by sharpening the theorem. There's no solution which is a core model. So remember, the intermodal program was trying to build core models. We're trying to get to a supercompact cardinal, but you can't. So the main goal of the intermodal program has to be revised. And the goal is now to construct strategic core models for all large cardinal axioms. But that's vague. So first of all, what are supercompact cardinals? Here's the definition. 15 minutes. So if kappa less than lambda are uncountable cardinals, p kappa of lambda, p is reminding you of power set, but it's the subsets of lambda that have cardinality less than kappa. So if I dropped the kappa, this would be all subsets of lambda. The kappa says restrict the sets of cardinality less than kappa. Now we're going to look at ultrafilters on I, that's our index set. So this ultrafilter is a subset of P of I. It's kappa complete if it's closed under intersections of cardinality less than kappa. That's an additivity requirement on the dual ideal. It's fine if for all alpha less than lambda, you look at all the points in our index set to which alpha belongs, that's large. That's a filter. And the ultrafilter has to extend that filter. Then there's a technical normality requirement. If you have a function from p kappa of lambda to lambda, if for u almost all sigma, f of sigma is an element of sigma, so it's a choice function almost everywhere, then it's constant on a set of measure 1. That's the normality condition. And then the definition from 67, due to Reinhardt and Soloway, suppose kappa is an uncountable cardinal. Kappa is supercompact if for all lambda bigger than kappa, there's a kappa complete normal fine ultrafilter on p kappa lambda. A fine ultrafilter can't be principal, so I don't need to say non-principal. All right, so now we can redefine the intermodal program. Suppose A is a set of reals and L of A in our models AD plus. We could simply ask, is it possible for there to exist an ordinal theta such that if I take the Hod of L of A in R and intersect it with V theta, it thinks it's a supercompact cardinal. I mean, we have Woodin cardinals in the Hod, so maybe there are rank initial segments of the Hod of L of R and R that think they're supercompacts. But where should we look for A? So we don't want to look at arbitrary A. We'd like to restrict the A's we want to look at. And the relevant restriction from almost 30 years ago is a notion of a set being universally bare. So A is universally bare for all topological spaces omega, for all continuous functions from omega to R. The preimage of A by pi has a property of bare in the space omega. So it's universally bare if it is universally bare, no matter what. So if you universally bare sets are clearly have the property of bare, you just take omega equal R in the identity function. But if you take omega to be the measure space, the measure algebra, stone space for the measure algebra, you get Lebesgue measurability. All the usual regularity properties flow from universally bare. The universally bare sets are the ultimate generalizations of the projective sets. Suppose there's a proper class of Woodin cardinals, and A is universally bare. By Martin Steele, A is determined. By Steele, A has a universally bare scale. And then I showed that every set in L of A and R is universally bare, and L of A and R is a model of AD plus. Okay, so the important thing about the universally bare sets is they're handed to you by V. There's no construction from below like the projective sets or L of R. They're just a feature of V. So now we could ask, assume there's a proper class of Woodins, A contained in a subset of reals, and it's universally bare. Can there exist theta such that pod L of A and R intersect V theta thinks there's a supercompact cardinal? L of A and R is a model of AD plus, so this is a specialization of the previous question. But now we need to ask, well, where should we look for A? You know, we said, all right, we're going to restrict to the universally bare sets, but we'd like to do better. So there's a ceiling theorem, and that leads us to a canonical model of AD plus. Suppose delta is supercompact and there's a proper class of Woodin cardinals. Suppose I have two generic extensions of V, V of G contained in V of H, and V delta plus 1 is countable in V of G. So the first generic extension has collapsed the set to be countable. This is some arbitrary further extension. We first focus here, V of G, the universally bare sets of V of G, that's what that is denoting. We let that be the universally bare sets of V of G. We let that be the universally bare sets of V of H. Sorry. Then the following hold. Now we're first going to focus on this. If we construct from the universally bare sets, that's putting all the universally bare sets in at the bottom, working in V of G, and we look at the sets of reals we get, they're all universally bare. So the universally bare sets are strongly closed. More remarkably, there's an elementary embedding from this structure that we get from the universally bare sets of this model to the corresponding structure from the universally bare sets here. So what is this really saying? After a sufficient forcing collapse, in other words, you make V delta plus 1 countable, the structure L of the universally bare sets given by the universally bare sets is completely sealed with respect to any further forcing. You can change the structure, but you can't change its properties. Change the structure by adding reals. So we now have a canonical model, a virtual canonical model of AD plus, and it appears after a collapse. So now we can sharpen our question still further. Suppose there's a proper class of Woodin supercompacts. Then after collapsing to achieve sealing, like, must there exist an ordinal theta such that M intersect V theta satisfies ZFC, M intersect V theta satisfies there as a supercompact cardinal, where M is the HOD of that AD plus model. So now we're looking at one model. And the question is the same, but for all large cardinals. So we have one model to look at, and we're just looking at rank initial segments of that model. I'm almost done. I have 5 more minutes. So let's go up to the ceiling. So large cardinals at the brink, and that's the Kunin inconsistency. Assume the axiom of choice, there's no non-trivial elementary embedding from V lambda plus 2 to V lambda plus 2. That's an embedding that preserves truth. Non-trivial means it's not the identity. Okay, so we can't, if we're going to have the axiom of choice, we can't do that. So we step back from the brink. Axiom I0, there's an elementary embedding from L of V lambda plus 1 to L of V lambda plus 1, which is not the identity on V lambda plus 1. And a slight variant, I0 plus, axiom I0 holds at lambda, that's this. But now we require that V lambda is an elementary substructure of V, and that's a scheme. And the idea is axiom I0 enriches V lambda, but then if V lambda is an elementary substructure of V, that enriches V, that makes V lambda plus 1 more complicated, and so we're cycling. Okay, why axiom I0 plus? From slightly over 10 years ago, suppose ZF plus axiom I0 plus holds that lambda is consistent. Notice there's no choice here. Then so is ZFC plus axiom I0 plus. So the axiom is equal consistent with its version with or without choice. And so that suggests that the Kunin inconsistency doesn't extend to I0 plus. And in particular, it doesn't extend to the weaker axiom I0. So this theorem says that if you in ZF without choice, if you have axiom I0 plus, then you can get to a model of ZFC where you have axiom I0. So there's no choice problem with axiom I0. Well, why axiom I0? Well, if you take Kunin's proof and change it, you get a theorem. Suppose axiom I0 holds at lambda, then the axiom of choice does not hold in L of V lambda plus 1. It's a fragment. Axiom I0 was first formulated 40 years ago as a transfinite generalization of AD. The intuition was that V lambda plus omega is like V omega plus 1, which is the reals. So the AD is the existence of the embedding. The main application for introducing the axiom was the theorem that if axiom I0 holds at lambda, then L of R models AD. And that was the first proof of AD L of R, even of PD, from ZFC large cardinal axiom. And one of those weird coincidences in the development of mathematics, this theorem was proved a year before it was realized it was going to be obsolete. In fact, a month before. It was just some weird timing issue. So I0 kind of faded away for a while, but there are deep structural analogies between L of V lambda plus 1, assuming axiom I0, and L of R, assuming AD holds an L of R. And this has been extended to generalizations of axiom I0 and ADR. So I0 is coming back into the story. All right, I only have 2 slides left. Axiom I0 plus and sealing. Suppose axiom I0 plus holds at lambda, then lambda is a limit of supercompact cardinals. And that's because V lambda is an elementary substructure of V, and axiom I0 thinks implies that V lambda thinks there's a supercompact cardinal. And so by the sealing theorem, if we collapse lambda, then we seal the UB sets. We have our canonical model of AD plus. And then we have Kramer's theorem from about 6 years ago. Suppose that I0 plus holds at lambda and we collapse lambda. We look at the UB sets that belong not to V of G, but to L of V lambda plus 1 bracket G. So we cut down the universally bare sets. Then for every subset of V lambda plus 1 that's in L of V lambda plus 1, there is a set in that gamma such that X is definable from parameters of that structure. So unpacking that, what this says is that L of V lambda plus 1 is deeply connected to the sealed AD plus model, L of gamma infinity G. There's some very tight connection. It's rather remarkable that the subsets of V lambda plus 1 that are in L of V lambda plus 1 are connected in any way to sets of reals in the sealed model after collapsing lambda. But that's what this theorem is saying. Okay, so now last slide. This now brings us to 2 conjectures. First conjecture is that suppose axiom I0 plus holds at lambda and that the UB sets are sealed. Then the conjecture is that the HOD of the sealed model is a strategic extender model. Or if you want, you could say, suppose axiom I0 plus holds at lambda, we know there's a supercompact cardinal, so we know there's a virtual canonical model of AD plus. This is saying the HOD of that virtual canonical model is a strategic core model. Proving this conjecture achieves the primary goal of the AD plus, the current primary goal of the AD plus duality program. Second conjecture then is suppose I0 plus holds at lambda and gamma infinity is sealed. We can get that by collapsing something less than lambda. Then the HOD of the sealed model thinks axiom I0 holds at some capital. Well, that would achieve the primary current goal of the intermodal program and much more. So we now have two very specific conjectures to focus on, and there are a lot of tools to attack these conjectures, a lot of progress on this conjecture. This conjecture is looking a little less mysterious, but if this conjecture is true, it would be astonishing if this conjecture were not true, given Cramer's theorem. So that's where we are now. And I think there's reason to be optimistic that in the next few years, a lot of progress will be made. Thank you.
So thank you, Hugh. So are there